So today we're going to kind of return to a subject that we've talked about before, which is balancing reactions. In this particular case, though, we're going to balance this special kind of reaction where we see electrons moving from one species to another. And then we have those changes in oxidation states. And what you'll hopefully notice is these things are slightly more complicated than a normal chemical reaction balance. And one thing that you should definitely do is take a look at either the page in your book that has these steps or the resource guide that I've posted. There's also an additional resource guide that has a bunch of questions that I don't know where I put. But that's what I'm going to use to kind of go through and just show you how you do each one of those steps that the text and resource guide delineates. So here's the reaction that we're going to take a look at, and one of the important things to recognize is that you kind of do something a little different depending on whether you're in acid or if you're in base. So this very first example will be in acidic conditions. The only difference is in basic conditions you have to do one additional step. So the first step, and I'll put a little more detail in here than I necessarily have to, just because I'll treat it kind of like we're going to be taking maybe a fiesta of knowledge at some point in the near future on this stuff. And so the first thing we're going to do is we're going to break it into two half reactions. And by necessity, both of those half reactions, one has to be an oxidation, one has to be a reduction. It doesn't necessarily matter that I assign those, and I can still do that. I can still do the balance without actually having done that. But it's so important that you guys recognize these things that I'll also highlight that. So obviously, I have some sort of half reaction that involves a phosphorus and another half reaction that involves an iodine. So the very first step is we're going to split this into two different half reactions, and I'll hopefully do it in such a way that we can still read it on the video pretty easily. And so the first thing I'll do is I'll just very simply write out the half reaction as it must occur. And so what I'm going to do as well is I'm going to identify whether or not this is an oxidation or a reduction, and then I'll check to make sure that based on whatever my choice was, that the other one is the opposite, if that hopefully makes some sense, right? You have to have a reduction and an oxidation. You can't have two oxidations or two reductions. If you do that, chances are you're never going to end up with a balance and you're going to get super frustrated. So the first thing I'm going to do is I'm going to go to probably the easiest one to recognize in terms of a change in oxidation state. And that is this one, right? Because I can see that this iodine must have a zero oxidation state, and that is obviously a -1 oxidation state. So that is a gain of electrons, and I say oil rig, right? Reduction is gain, or oxidation is loss. So if I'm gaining electrons going in this direction, that must be the reduction. And I'm just going to label this an oxidation, and we're going to hope that the numbers work out. And if the numbers don't, you know that you've made some sort of mistake. So let's see, probably the easiest oxidation state to assign for phosphorus is on this one, right? And so if we assume that oxygen's a 2-, and there's two of them, that's 4-, and then we've got 3+ charged hydrogens, which means that phosphorus must have an overall oxidation state of 0 in this particular case. And so we look over here and we're going to make sure that this thing becomes, more positive, right? Because that's what should happen in oxidation as we give up electrons. And we look at this and we say, well, if hydrogen's a 3+, by the way, it can be a 3-, so that might be a little confusing. In this particular case, they're close enough in electronegativity that it kind of creates some problems, but that thing is going to be a -3. The good news is, as I go through the steps of this process, if I've screwed up either my oxidation or my reduction, I'm going to be able to see based on the way this thing works. So let's go through the next step. Next thing I'm going to do is I am going to balance everything that is not an oxygen or a hydrogen, right? And so here my phosphorus is already balanced. Here I see that I need actually 2 iodines, and I'm not going to worry about the charge. That'll come later. I'm going to make sure that I've got everything balanced in terms of those non-O and H elements. And now I'm going to balance oxygens, and I have to use H2O using this method to balance oxygens. look over here, I've got 2 oxygens on the right side. Must mean that I have 2 oxygens over here. And I'm going to put 2 H2Os over on this side, right? And keep in mind, that's where I'm balancing oxygen. Over here, there is no oxygen, so I don't have to worry about it. So I can move on to the very next step of that resource guide, which is to balance hydrogens at this point. And we're going to use H pluses, right? And keep in mind, this is an acidic media, so that's perfectly okay to use H pluses. This one, I mean, you have to be careful about your counting. So what I see here is I see 4 hydrogens plus another 3, that's a 7. I've got 3 hydrogens here, so I obviously need an additional 4 H's, and I kind of purposely chose this one so that I didn't have to have it fall off the edge of the board here. Hopefully we don't have any hydrogens there. At this point is a pretty important step, and this is the point where we're going to be able to officially assign whether something's a reduction or an oxidation. The idea of a half reaction is one reaction will give up its electrons, and then the other reaction will accept them. But what must be true when we're all said and done is that that has to be equal, right? You can't give up more electrons than you accept, and vice versa. So, keeping that in mind, we're going to use charges to help us out, right? Right now, as I look at this thing, this side has a 0 charge, and this side over here has a 3+ charge. I have to use electrons in order to balance that charge, and electrons are negatively charged, right? And so if I am going to end up with a 0 charge, the only way that I can do that is balance out these additional 3 positives with exactly 3 electrons. And at this point, I say, aha, I've just confirmed the fact that my oxidation states were right, the fact that I see electrons being produced in an oxidation reaction. I do the same thing down here, and what should be true is that when I balance these charges with my 2 electrons, that's an E, not a C, that you should notice that, in fact, this is a reduction, right? I'm gobbling up or gaining electrons as I go from left to right, and that confirms, in fact, that I have a reduction. So, now, well, what do I do with this, right? I've got 3 E- charges over there, if hopefully you can see that, and 2 E- charges right here. Electrons have to be balanced before I can put all this stuff together. And the way that I'm going to do that is very much like in math class. You pretty much go to the highest common multiple, right? And so what I'll do is I'll multiply this whole entire thing by 2. This, I'm going to multiply that entire thing by 3, and you'll notice when I'm finally done writing all this out that the electrons are equal. I'm going to combine them, and then after that I'll kind of simplify it, and then we're done. Okay, so hopefully I've written that all out so that you can actually see. And you'll notice that I've produced 6 electrons over here, and I gobbled them up over here. So what's going to happen when I combine these both together is that these are going to just disappear. And the other good thing is anything that I see on the left side, I can also cancel out with something I also see on the right side. But here, there is nothing in common, right? Sometimes what will happen is you'll have H2Os on one side that you can cancel with those on the other. Sometimes you'll have H pluses on one side that you can cancel on the other. Here, though, I'm just going to combine it as written. I'll erase this up here, and we'll have the answer to the question. This example obviously is going to now be in base, so there's one additional step. This will also provide a little bit more practice with actually following the steps we just talked about in the acidic version. I'll just kind of draw everything out, and you can pause the video any place that it gets confusing. So obviously, first thing is we got to split this apart into our 2 half reactions. At this point, I'll check the oxidation states. So this guy, right, 4 oxygen 2 minuses gets me to an 8-. So that is a 7+. This guy is going to a 4+. And that means that this is now my reduction, right? Because I become some number of units more negative. So this is the reduction half reaction. This must therefore be my oxidation half reaction, and I'll make sure that that is in fact true. If this is 4 2 minuses, adds up to an 8 minus, therefore this side must be 6 plus, which means each carbon is a 3 plus, or plus 3. Here I've got a carbon which is a 4 plus, and in fact it does go up by 1, the oxidation state of that carbon. So in fact it is an oxidation state, or sorry, an oxidation half reaction, meaning it's giving up electrons. Next step, we're going to balance all non-oxygen and hydrogens. So manganese is balanced there. We're going to have to put a 2 in front of this to take care of the 2 carbons. Next step is to balance oxygens with H2O. Got 4 oxygens there, 2 oxygens right there, which means I need 2 more oxygens over on this side. And this guy right now has balanced oxygen numbers. Move on to the next one, which is to balance with H pluses. So it looks like we need 4 H pluses over here. Come down here, we have no H pluses, we're good to go. Very next step is to balance the charge with electrons. At this point, I've got a neutral charge here, and I've got a overall 3 plus over here. So that means I'm gonna need 3 electrons over there. Notice that in fact this is a reduction, right? It's consuming electrons going that direction. Same thing down here. I've got just that 2 minus charge, which means I have to put 2 minus charges over there. In fact, it is an oxidation. I'm going to go through and multiply these guys together in order to get to, once again, 6 electrons. Multiply this by 2. Multiply that through by 3. And I'll write the results and we'll do some simplifications. And we're going to go ahead and simplify everything that we possibly can, which doesn't look like too much here. And I think that's pretty much it. Okay, so now what I'll do is, remember, this is an example in base. So what I'm going to do is I'm going to erase a little bit. I'll combine everything together in now that we're in acid, and I'll show you how to deal with the fact that we're in base. All right, hopefully that's everything, and hopefully it's somewhat readable. So the very next step is we're going to add OHs, OH minuses, to get rid of all the H pluses. But the thing is, if I add something to one side, I have to also add it to the other. So what I'll do is I'm going to add 8 OH minuses here. And I'll remember that I have to add 8 OH minuses over here. And keep in mind that when you do a neutralization like this, really all I'm doing is turning every one of those H pluses into a water. And we're pretty much all we have to do at this point is to just now get rid of, or simplify I should say, anything that I have on both the left and the right side. So the fact that I had 4 H2Os over here and 8 here, I now can make that just a 4. So I'll press the pause button and I'll show you what we have all together. And hopefully that'll make balancing things in base pretty straightforward. All right, there's the final answer if you're interested. And I should mention one other thing. When we get to that very next video lecture and we start working with galvanic cells, you can actually go to the half reaction step and add your OH minuses at that point. So the reason you might do that is because you need to, let's say, come up with the reduction potential for some reason, and that'll become a little bit clearer. That very last step, I usually, if I can, wait until the very last step. Sometimes you can do it here. It doesn't really matter either way. So have fun.